I had some requests to look at this problem. This is problem number 3 from discussion 4. And what we have here is we have a sphere of radius r that's got a total charge q on it. And then we've got a spherical shell that's centered at the same point that the sphere is. It has a radius of 2r that's got a total charge of negative q on it. And what we want to do is we want to go and find the electric field for all 3 regions. For r less than r, r between r and 2r, and then finally r greater than big R. And so the first thing, just to discuss here, so in a case like this where we have spherical symmetry, our Gaussian surface is going to be a sphere. Okay, so it's going to be a sphere, and because of the symmetry, our electric field is going to look something kind of like this on the sphere. And this is a key point because this is a very powerful idea that's going to make this problem a lot easier. And so we're going to have some sphere, usually we'll call the radius of that sphere r, and the point is that the electric field has 2 key features. It's 90 degrees to the surface and it's constant. And you can, if you can sort of argue this to yourself in a couple different ways, so if we make this, Gaussian surface around some sphere that's uniformly charged, like this one is here, right, then first of all, there's no reason that the electric field here should be any different from the electric field over here. They're a distance r away from the object, and the object has spherical symmetry. And so there is no reason that those electric fields should be different. So that's the way you can argue that they're equal. Now, they could be pointing inwards. Maybe it's a negative charge. They could be 0 because there is no charge, but they have to be the same. So we'll just in general start with this idea that they're pointing outwards positively, and then let the sort of question lead us where to go. And the other thing is that they have to be pointing radially. And this again because of the symmetry, right? And so you can't have any situation where like the electric field is pointing sort of off at an angle or something like that. Okay, it has to be pointing at 90 degrees. And this makes our life a lot easier. So basically what it's going to do is it's going to make this left-hand side of the integral the same in all 3 cases. And so here's our integral. If we wanted to write this out with our definition of the dot product, we'd have the magnitude of E, the magnitude of this thing dA, times cosine of the angle theta. This angle theta is the angle between our electric field and this thing that we call the area vector. And so the area vector points 90 degrees to the surface, and so the angle between that and our electric field, which would be our theta, is 0. So cosine of theta turns into 1, so that makes that much easier. And then what we can do is, since the electric field is constant everywhere, I can just pull it outside of my integral. And so my integral here, this integral then just turns to be a sum of the areas all over this Gaussian surface. And so it's the total surface area of a sphere. And so what we end up having then is our electric field times our area. I'm just going to drop the vector signs and everything here. Just this is the magnitude of our electric field. And what I'll typically do is I'll sort of draw, so it's the electric field as a function of r, and the area with this spherical symmetry, the surface area of our sphere, is always going to be 4 pi r squared. So in all 3 regions we look at, we can start right away with that same expression. And that makes things just a little bit easier. So we'll start doing this with r less than big R. And so if I look at my picture, my Gaussian surface will be inside the sphere. And we did an example very similar to this in class, so you can go back and check your notes. And so I'm going to call this radius r inside here. But it's the same sort of idea. And what we can do then is just, again, automatically say, okay, well, I got my electric field as a function of r times 4 pi r squared. So my left-hand side turns out to be the same in all these cases. And so now Gauss's law is going to equal my Q enclosed divided by epsilon naught. And so my Q enclosed here, well, there's lots of ways to kind of think about it. One way is to create a rho. Rho is the charge density of this sphere. It would be Q divided by the total volume of the sphere. And so the sphere has a charge Q, and the total volume of it looks like this here. That would be our definition of rho. And so to get the Q enclosed, so I'll write this constant guy in here. The Q enclosed, maybe the fastest way is to say rho times the volume of my sphere. And so it's really important here. This turns into a game of knowing which R is which. And so it's rho times the volume, right? Rho is charge per volume, times by volume gives you the charge inside that volume. And so we got to make sure we use the R cubed, the little one. If I then solve for my electric field as a function of R, I get 1 over 4 pi epsilon naught, so that's the 4 pi, the epsilon naught piece, and I have rho times 4/3 pi R cubed over R squared. And so I can clean this up a little bit by calling this thing our K constant. Here's my rho, 4/3 pi. Now what'll happen is you get some cancellations here, and it turns out to be 4/3 pi R. Now that's a totally fine way to write the answer, but typically we like to get rid of that rho. And so I can just plug in over here my expression for that rho. And so I get K, and for my rho I get Q over this 4/3 pi capital R cubed. And I still have this 4/3 pi R, and so you get all these 4/3 and pi's to cancel. And so I get something like KQ R over R cubed. And the key is, as a function of R, this thing is linear with R. So as that circle gets bigger, all right, the electric field gets stronger as you get further out from the center. That R cubed, of course, is a constant, as is the K, as is the Q. Now, so the next piece, and then doing this, would be to look at the surface in between. And so our Gaussian surface would be somewhere like around here. And again, we always call our Gaussian surface to have the radius little r. That's just the convention that we use. And just like last time, my left-hand side turns out to be exactly the same. So it's that same thing. E is a function of r times 4 pi r squared. And again, now my Q enclosed is really easy. It's just that total Q over epsilon naught. And so this turns out to be not too bad. And so I get 1 over 4 pi epsilon naught Q over r squared. I get the equation for a point charge, right? So in between the regions, it's just the electric field due to a point charge is what we get. And what's also really nice is you see that there's it's a nice smooth transition. So again, this is for r less than 2r and bigger than r. So our equation for r less than r, right, we just did it, turned out to be something kind of like this. It was ER and it equaled K QR over r cubed. And so if I take this and plug in the capital R, so sort of find this at the extreme point, capital R, I get KQ capital R over r cubed, or KQ over r squared, which is the same thing I'd get over here if I plugged in r squared. So you see from that transition at that point R, between the two equations, they're continuous. And that's a nice thing to have happen. And finally, our last region would be r greater than the 2r. And again, we're going to do the same kind of setup. Now what we want to do here is draw our, again, Gaussian surface outside of this. And I apologize, my Gaussian surfaces are not looking too good. But it's a Gaussian surface outside, and here I'm going to again have my, call it radius r. And this one turns out to be even a little bit easier, just mathematically at least, ER 4 pi r squared, because now the charge enclosed is 0. Because that sphere has a total charge of negative q, and that, the sphere has a charge of positive q, and that shell has a charge of negative q. So this turns out to be a total electric field of 0. Right. So that's how you would do a problem like that. There's some examples in the book of some different ones, and we went over some examples of this in class. So I definitely advise you to go over this. The good news is there's only so many situations that you can actually do this with. And again, it's one of those things where the conceptual part, I think, is much tougher than the actual math you end up doing. So doing some examples and thinking through is the best way to go.